In this video, I'll be using CST to calculate the Lorentz force detuning of the Tesla cavity. And then I'm going to be comparing the value I get from CST Studio to the value in this paper. I think I would also link the paper in the description. So if you scroll down to page, I think I've already shown this paper in maybe a previous video before, but I can't remember, so I'll just show it again. So if you scroll down to page 13, you'll see some figures of merit and design parameters that are presented in table and that are kind of useful or give you an idea of how the cavity works. So today I'll be calculating the Lorentz force detuning of the Tesla cavity, the actual Tesla cavity, because it's 9 cell, and with the dimensions also from this paper, although the dimensions are approximated. So I would also link a paper in the description that shows a more accurate results, more accurate dimensions of the Tesla cavity. I hope I don't forget. So today, yes, we'll be calculating the Lorentz force detuning. So Lorentz force detuning occurs when of course, we want to accelerate particles, and for that we need high gradient accelerating fields. So what happens is that these high gradient accelerating fields change the shape. I mean, not change the shape, like creates forces on the internals of the cavity, and then this kind of results in some little displacement, some little change in the dimensions of the cavity, and this in turn causes a frequency shift of the cavity. So that frequency shift is what we're going to be calculating. So for this, I already have the Tesla cavity here. So for this analysis, we'll be doing Eigenmode analysis, and then so we'll be using the Eigenmode analysis, which is in the high frequency problem type, and then we would also be using the mechanics, so the structural mechanics calculation. Structural mechanics calculation. So first of all, we calculate the eigenmodes, and for that there's already a tutorial for that. I'll try and link it in the description so that it just appears where I said I'll link it. So okay, enough of talk. So it's already set up to Eigenmode solver. So I already have the Tesla cavity opened, cavity geometry opened, and then my parameters. So I go to for this simulation, sigma is not required, so maybe I'll just delete it. Yes, so I just have these. Okay, and you could also just copy I could expect this, you could also just copy the more precise geometric parameter values here. Oh, I can't minimize this order, so I'll just scroll so you could pause and check, but then I'll still link the paper. So I already have my geometry, so no need for any further modeling step. And then I go to frequency. I want to calculate just for the fundamental mode frequency, so your TM010 pi mode, but then it wouldn't have to calculate for the other mode. So I'm going from 1280 to 1305. The operating frequency is 8300, so this should be enough. And background is spec, and boundary conditions, electrical, and then magnetic at the ends, and no symmetry planes. I mean, I could use symmetry planes to simplify the problem, but now I'm not sure if the mechanical analysis allows for symmetry planes. I think it should allow, but I'm just going to run it without symmetry planes. You could try running with symmetry planes. So okay, and we are all set up for Eigenmode simulation. So I want 9 modes and frequencies above 1280 megahertz, because my system here, if you can see it, is in millimeters. So here, millimeters, megahertz, nanoseconds. So my units Now what else? Yes, that's that. I could also change this to general lossy. I don't want to refine tetrahedral mesh. Oh, before that I check to, okay, I think I'll just do the automatic refinement so I get accurate results. I mean, the goal is to get as close as possible to this, so like really doing accurate analysis. So 9 modes and apply, and then 1280, and then refine tetrahedral mesh. So I set the minimum frequency variation so of this should be maybe 1e to minus 5. Number of passes, okay, 6. I think 6 is okay. 1e to minus 5, I make it 1e to minus 6. So number of modes to check, I mean 10, but then it's just 9 modes, so it's going to check for 9. So that's that, and I'm going to run it and pause this video and come back when the simulation is done. So I click on start, and yes, it's starting, so I'll be back in or shortly. Okay, so the simulation is done, and although we didn't quite get to 1e to minus 6, if you should look at the messages, you would see that yeah, the maximum delta f, I think, so yeah, it just gives a warning, the maximum number of passes reached mesh adaptation stopped, and then the maximum relative delta calculation is 6e minus 6. So I think that's pretty good. So you could also check from the adaptive mesh setting, the solver time, the mesh cell, and then the error. So it's not up to, I think, let me see the minimum. So 5.5e to minus 6, I think that's pretty good. And then you check the mode frequencies. And yes, so now we have a result from the Eigenmode, and then we could have a look at our fields just to make sure. Oh, this is actually 7. So the frequency range was not okay sufficient for 9 modes, but I hope that we have accelerating mode. Yes, that's this. So 1 to 9 points. 1 to 99.99 to approximately 1,300 megahertz. So I'll take that. And now what we need for the, because this kind of a coupled electrical and mechanical simulation, so I could also close the plot. So what we need is the Lorentz force calculated on the surface. So I have I think it's from 2D 3D results now. Miscellaneous, is that mix or misc? I'll go with misc. Okay, so miscellaneous, and you go to Lorentz force computation. So when you click on this, this template compute the Lorentz force for all 3 eigenmode simulation. Lorentz force results can afterwards be imported as a source into the mechanical solver, so it says it here. And also be careful, it only supports tetrahedral mesh. So I think if you try to run this when you use the hexahedral mesh to solve the Eigenmode analysis, you may get an error, so be careful. So okay, and I evaluate it and wait, and that's all. So if I should go to tables, then I see my 0D results, and then I have my Lorentz force computation, but then that's not this. So I should go to I should have, yes, so Lorentz force density. Yeah, that's what I need, not this one. So I have the Lorentz force density for all the modes that I calculated. So this is what I would be importing into the mechanical system. So yes, so you have this, and you could also view it as a contour if you want, but then I think it's okay. So that's the only thing we need. So I go ahead and save this. Now what I could do is I could either copy this project, I could either copy, so I have my Tesla cavity saved here. I could either make a copy and then create a new, so have a new CST file and then change it to mechanical. But then one other thing I could do is go to schematic, so I could just close this and close this too. So I could go to schematic and then navigation tree, and then task. I could add a new task under the same file, but then creating a different simulation. So because of course, if I should try and change this from, so if I go back to 3D, if I should change this from to mechanics, then I'll delete my Eigenmode results, which is what I do not want. So I go to schematic navigation tree and then I add a new task, and I want a simulation project. So simulation project, and okay, then I select my geometry and click on 3D model. So I've selected it and then create simulation project. So I'm going to call this mechanical structural analysis. Mechanical. I'll just call it mech. Tesla mech, or structural analysis. Yeah, structural or mechanical and mech. Yeah. Okay. Then the project type, it's in thermal and mechanics, and then structural mechanics. Yes, that's what I want. So, and then block. This is not important. Yes. So it creates a new CST project, but then it's still under this now. I think when it's done, I'll show how it organizes it. So I have a new project which is mechanical, and you see it's already set to mechanical, but then I could change the problem type anytime, and then when you go to the folder containing it, you still have just one Tesla file, but then when you open inside, you go to SP, then you see Tesla mech. So if you create other tasks, so you could create Wakefield analysis following the same method and everything, and then it just saves into this place. So still under Tesla. So now we have, I have to turn off this working plane, it's annoying. So we have a vacuum, but then for the mechanical analysis we need a material, and also with material properties, and also we need the material, and what else do we need? I think we need something else, but then I have forgotten. So we go to the setup. So home, it's already set up to structural, and modeling, we already have the model. Now simulation, we would be making use of this, but then first we need the material, and then we need to create a shell out of this and define a thickness. So parameter list, I do not already have a thickness, so I could parameterize it. Remember, always parameterize. So thickness, so I'll use a thickness of I don't know if they recorded the thickness here. Let's see, where's that paper? Wall thickness. I'll maybe go ahead and pause, or just do a quick search. If I can't find it, then I'll pause. Yes, wall thickness of 2.5 millimeter. So yeah, got it. It's stored for this. The computed frequency shift at 25 megavolts per meter amounts to 900 hertz for an unstiffened cavity of 2.5 millimeter wall thickness. Okay, yeah, that's what I'm looking for. So we need a wall thickness, and this is 25. Now because it's parameterized, you could of course run for the detuning for different different thicknesses. So, and then we need to shell, so still preparing our model. So F to select face, and then F again to select this face, and then I go to shape tools, and if you encounter this and then you can't access the shell sort to thicken, it means you haven't selected. So I think maybe this works. Yeah, you haven't selected the solid, so let's see the level at which it starts working. Okay, it still does not work, so you have to select the component. Let's see, still doesn't work. Okay, so you have to select the solid. Oh, so it works for this, but then the problem is that it's you'd only shell this. So first of all, I have to boolean, so I have to deselect, so D to deselect or escape. Wait, something is wrong. D is not working, escape. Okay, I save first of all, and the select is not work. Okay, now it works. Maybe I needed to save that. So I go to components and I either click on boolean plus, I could also click plus on my keyboard. So I just click this, and so it adds everything. So now I can shell. So F, and then select the two faces and shape tools. Now it's not grayed out. So, and then you want to make the direction outside and thickness 2.5 millimeters. Oh no, why would I do that? Thickness, yeah. Oh, I think I spelled that wrongly. I'll just spell it correctly and delete it. So thickness, yes, so thickness is 2.5 millimeters outside, and okay. Okay, takes a while. I don't know why. Oh, come on. Oh, um, I think something might be wrong. Because I can access this and then this is not going away, so I just delete this. So I have this attempted an unsupported operation. No, it was supported. So yes, now I can see through. So it has been shelled and then the thickness is 2.5 millimeters. Now we need to apply material because this is still vacuum. So I don't know exactly what material they applied. Let's see, we used. So let's go to F. It's niobium, of course, but then I don't know the exact properties of the niobium. They reduced to this for 1.3. Okay, and also its continuous wave, I think it was mentioned. So they reduced to frequency shift of 500 hertz when you have long RF pulses. So I think for this one it should be for continuous wave. Now I do not know exactly what material properties the niobium has, but I know that CST has. Or did I create? Now I can't remember if I was the one that created the niobium material a while ago. It seems so. That's the niobium material that I'm going to import now on CST Studio. But then I'm going to show the properties in case, because now I can't remember if it comes with CST Studio. So I'm going to show the properties just in case. So I go to this and oh, I could also rename this to Tesla. Left cup doesn't make sense. Tesla. So I go to this and assign material and color, then I go to load from library. I'm just going to put niobium. So I think this came by default, yes, because yes. So because if you look at the folder, then you see that it's installed on yeah, CST installation path. So I think this is I'll just use. I think they should both be the same. I'll just take this bake out. I think the mechanical properties of the two of them should be the same. So I'll take this and then okay. So we have our material setup. So we are done with the modeling. So we have an actual cavity. Now let's set up the boundary conditions. Now the boundary conditions that will be suitable for this analysis is okay. We assume that at both ends it's long enough, although this is not quite long enough. I could extend it, but then I do not want this to run forever. I could extend the pipes just a little bit more, but I think this should be okay. So we assume that the two ends are fixed and then this part is allowed to move. So that's the boundary condition. You could also apply just to one end, but then that would, I think that applying at both ends, fixing both ends, it's actually a better approximation than just leaving it at one, just fixing at one end. Okay, but maybe, yeah, that may be wrong, but yeah, I think that's better for now. So I go to F, I click on F to select face, and then I double click this, and then I apply the displacement boundary condition. Oh, I didn't need to select the face first. Once I click on the displacement boundary condition, I get into the face selection mode, and then I can double click on that face and then enter. So I want zero displacement, so no displacement in the X, so it's like fixing it. I think in some other software you'd see fixed boundary condition, something like that. So I apply the same to the other face, and then displacement boundary condition. So yes, and enter. Okay, I'll do that again. So displacement boundary condition. Now select face for displacement boundary in main view, or press escape to return or escape to leave this mode. So I select the face, and then I press return to select it. So return is enter, and yes, this is what I have also fixed. Now in another video I would show how to do a pressure sensitivity analysis, and that's when you need your traction boundary condition. So your traction boundary condition could create a uniform force across the internals of the cavity. So you could okay, I think I could just show it. So you could maybe select, and okay, I'll leave it for later instead. I'll leave it for later. The escape. For some reason my CST is misbehaving today. I just have to click on escape to leave this mode and then D to deselect. It's not working. I'll just leave it. So I'll show it in another video instead of showing it here. So now we need of course a field, a force field, and that's where we get from. So field import, we go to field import, and then the project is this project which you see here. But then if I had copied the Tesla and then worked with another file, then I would go to a different project. So select and then navigate to the project, but now it's still inside here. And then you see the appropriate input files already here from this analysis that we did. So we need for mode 7, because mode 7 is accelerating mode, so that's the force density for mode 7, and then leave the rest as they are, and then click on OK. So we have a field imported. Where is that? Yes, field source. Now yes, so we have a field source imported, but then yes, so that's it. But then okay, let's see. So that's that. And now to set up solver, let's say an accuracy of 1 to -6, and store result data, leave the other ones. And then now for the field sources settings, because CST Studio scales the fields to CST Studio scales the field values to an energy, a total energy of 1 joule. So our accelerating field, so if we should look at the E of this, it's not quite what we want it to be. So we need a factor to scale the field by okay, I think I'm getting this wrong. Your let's see, field source setting. So we need a factor to scale the Lorentz force by okay, I'll just show how to calculate it, but then I think it might be now I can't remember if it's a square. Maybe I'll have to pause to think about it a while. But then before that, let's see how to kind of scale our field values to what we need. So we need 25 megavolts per meter. So that's the tuning was the frequency shift was computed at 25 megavolts per meter. So we need to scale our accelerating field to 25 megavolts per meter. I think this video is already really long, so maybe I'll speed things up a bit. So we go to post-processing, so we need to evaluate accelerating field. So go to post-processing and yeah, we'll get the voltage. Tweet Eigenmode result and accelerating voltage of mode 7. I could just calculate for all the modes. Z direction, consider particle velocity. This is already in a previous video. You could so evaluate this. Should be done very soon, and I mean, I could have just made it one field, but okay. So yes, we got the accelerating voltage, and from this we calculate the E acceleration, which would be, we go to 1D and then mix, and then not Lorentz force computation voltage, and then so it's voltage divided by the length, the length of the structure without the beam pipe. So I would have that this should be 2 times 8, so each cell is L, so 2 times L will give for one cell, then times 8 n plus L, so the left end cup plus the right hand cup. I hope I have everything correct. Oh, and then this should be in meters, so I would have to change this to times 1 e to minus 3. I think this should be okay. So I call this EACC. So to maximum, so EACC is about 20 or 27.79 megavolts, and we need that 25, but then I'm not quite sure of this, so I have to calculate the E peak over E acceleration first just to check. So for that I would create a new surface. Yes, so I would select, so Control Shift S. No. Yes, and then I select this also, and then I'm going to go fast because there's already a video on this. So I go to faces, I click on create face from pick face, yeah, face 1. Oh come on, why is it slow today? I think that's okay, that's done, and then I go to my post-processing again and result templates. I click on, I mean you don't have to do this, but then I just want to be sure that I'm getting the right values, because then the E peak of air acceleration is independent of the accelerating field. It's just an independent ratio. So what I need is 2D 3D results, and then evaluate on arbitrary. I think it's evaluate on phase. Yes, evaluate on phase. So I need the absolute value, magnitude. So I need a maximum of 7, and yes, I think okay. So I need the maximum value and evaluate on surface. Yes. So make sure to click this, and so I call this E peak. So I could evaluate this. Oh, come on, you don't need to take so much time. No, I don't know how long this video is already. But then now I need to get, so general 1D mix, and then E peak of the acceleration. So A divided by B. E peak divided by acceleration. Okay. And then for mode 7 is 2.08. Okay, it's supposed to be 2 points. Wait, let me see. Now I don't know if this value they reported here, because it's supposed to be 2.0. is just for the mid cell or for the entire cavity, but I think maybe it's for the entire cavity. So maybe with maybe we'll have to refine our mesh even more to get 2.0, but I think yeah, this is close enough. So I just want for 1 to maximum, no to minimum. Yeah, so 2.0, I think that's okay enough. So that's just what I wanted to confirm. And maybe also, since we're here, I just do for H peak. No, I think this is okay. So we have that accelerating voltage is 27.79. So 27.79. So I think we should have a calculator. Yes. So this is 27.79. I want to scale it to 25. So I would have to do 27.79 to 78 divided by 25, so that's megavolts per meter, and calculate. So it's about 1.112. So that's the factor that we have to multiply with. Now I wasn't sure if there was a square or something, but then maybe we should look at the, I mean from the, so the electromagnetic field exerts a Lorentz force on the current induced. So this force, this resulting pressure, which is what we exported, so Lorentz force density is proportional to the square of the field. So that's why I was thinking it was a square. So it's actually the square of the value. So it's proportional to the square of the value. So we have to square, so multiply our exported field by the square of this value. So I'll just copy this from here. So Control C, and yes, so Lorentz force density, which is what you see here, resulting pressure, so that's the density, and has been so this has been changed. So I'll just click on F7 to update the entire project. Phase does not exist. Okay, I don't think that's a problem. Let's see. Okay, I hope that error wasn't serious. And yes, back to this. Where was I? So we've already set up the, oh, I think there's actually an error. The history is not positioned at the very last. Wait, coming, I think the error is with the faces. I thought about, so I see. So I'm going to hide this, and then let's see. The face does not exist. Oh, define displacement 1 2. Okay, updating from this model actually changed something. Yeah, I shouldn't have updated that, but it's okay. I'll just define the boundary conditions again. So peak phase, but then why? I know this one is not supposed to be here, but this is supposed to be okay. But nonetheless, I'll just delete it and set it up again, instead of trying to find out why that didn't work. That should have worked. So I hope we still have a thickness of 2. So I go to simulation displacement, and yes, and enter displacement of 0. And then on the other phase, displacement boundary condition of 0. Yes. And then field imports, and that's Tesla, and force mode density 7. And yes, that's that. So now for the setup solver, we go to accuracy. I'll just click on apply, and then field sources setting. So we had that value, and I'll just paste it and square it. So okay, and just to check again that is there. Yes, so that's it. So that scales our field. Oh, sorry, This is more than, so we're supposed to divide by this value. So we're supposed to divide by the square of this value. So it should be, oh no, not the square. 1 divided by, oh sorry. Since if it is greater, it's supposed to be 25 divided by 27.79278. Yes. So this value square. So scaling it down. Yes. Hopefully I didn't make any mistakes. And then I can, let's see, specials, nothing. Solver type, I think it should take iterative. And then, okay. What else? Adaptive mesh refinement. Okay, I'll leave that also. So I'll have to pause. So let's see 1 to minus 6, and then minimum to maximum. And 1, 2, 3, 4, 5, 6. Yes. So it might not get there, but let's see. And I'll start this and pause the video again. So the simulation is done. Before that, for some reason, when I ran it the first time, it didn't run, so I had to close this and open it again. I don't know, CST is misbehaving today. So simulation is done. 6 passes. I don't think it got to the. I don't think I got to the required. No, I don't know how to check. Okay, no, why would I say that? So that's this. I wonder what it checked. Error. Okay, the error is still relative. Error is still a bit large. I don't know if that is typical of the mechanical solver. This looks big, but then what's the unit? I don't know, but I think I'll just continue like that, and let's see. I could also look at the final mesh to see if it's okay. Let's see. Continue playing. 6. Okay, still a bit coarse. What can I do? What should I do? One thing I could do is to, refine it further. How many elements I have? I think I have 100,000. Refine it further, so at least I have maybe 2 cells here. But then I'll just continue with this, just not to make this longer. But then you could always refine it further. So yes, or for the adaptive mesh, you just set for more passes. So what we have is displacement. We have results from displacement, so 6. So this is the now I'm thinking if I have the right mode. Okay, I think I have the right mode. So let's see this. Mode 7, right? Yeah, mode 7 is correct. So I have the right mode, and then the maximum displacement is at the center. So yeah, so at the middle. I think it also has something to do with the boundary conditions. Okay. What do I want to check now? So this is the maximum displacement 0.00025 millimeters. So for the displacement, you could view as contour, and then you could also view as arrows. Yes, and then you could view as deformation. Now for this, there's something cool you could actually do with this. So we have this, and then I could go to displacement, then right click, and no, import properties, no. there's a way you could view the deformation, but I'll have to maybe look for it a while. I've forgotten. So this is deformation, and then you could this plot properties. Yes, that's it. So you should go to plot properties, and you could actually view the deformation. So I'm going to click show original model, and then maybe I so it is supposed to move, but okay, you can't really see it. Why is that? Let me check fields on plane, and then I could click on displacement again, and maybe I'll see it. Then I go to deformation. The selected plot is not available. Okay, for plane. Okay, so I mean where did I go just now? Plot properties. I mean this is supposed to move the curve to somewhere, but I can't seem to see it. Let me check at the end, see if I can see the displacement. I think if maybe displacement is too small, maybe I make it to 1000, and then let's see if I could apply to 1000, and then okay, you could see it's yes. Okay, so the scale, the displacement is quite small, so 1000 would mean 1 2 3 4, so I'll make it 10,000 to get a maximum displacement of 2 millimeters. So come on, 10,000. Oh, 10,000. Yes, so if I should drive this, then you could see some movement now, and then if I should uncheck original, maybe I take it up a bit more. Yes, so yes, I could also drive it more. Yes, so you could see, okay, this is a bit too much, but then you could see the deformation caused by the Lorentz force detuning. So it was just the scale, and you could also show original model. Yes. So that's it. And now this then you could also view the von Mises stress, and you could I think yeah, you could smart scale it, or you could reset scaling and then maybe log it, so you see the stresses and hydrostatic stress. I don't know what that is. Then your first principal stress. So yeah, displacement. This is the result we need to. This is the result that we need cutting plane now. So the displacement result is what we need to import back into the Eigenmode solver and then run the sensitivity analysis with this displacement. So we go to our main project, and then I mean if you're running this independently, then you would have to create another file, another CST file named Tesla, maybe Eigenmode with displacement, and import the field. But yeah, I'm just going to add a new task, and okay, I think I have to select, yeah, I have to add a new task and simulation project. I select the model, the 3D model, and create simulation project. So the project type is high frequency, and I need that Eigenmode, yes, and yes. Oh, I forgot to rename it. Nope. bother, I could rename it from here. So it's creating a new Eigenmode simulation. I mean, of course, I could take it back, but then, I mean, I could take my displacement back here and then run the analysis, but I don't want to do that. So I have this SP1, but then I could also rename it from here, and I'll call it Tesla EM with displacement. Weird name, but it's okay. Yes, so this is going to be the same as I want to take this off because it's quite annoying. So we are going to run the Eigenmode simulation again, so I'm just going to check my settings. Yes, and background, everything okay. Okay, and one thing to mention just before we proceed, I actually made a mistake maybe because when I run in projects, when I run CST simulations with project like this, I only leave this as my model and no analysis is done with it. Then I create my analysis separately from the model. So this would have helped avoid the situation where I created a surface, this face, and then it had to update this and then had some model problems with this. So if I just had the geometry and then for the Eigenmode analysis I created the software, it wouldn't have affected the main file. So just had to mention that. So now what else do we need? We have our boundary conditions, and then we need a field import. So I go to field import, and then what I need is I need field from Tesla mechanical. So it already automatically selects the displacement field for me, and I click on OK. So what else? So I think that's that. Then I go to setup solver, and for this I would have to switch to the default solver, because then and only then can I use the sensitivity analysis. I'm going to keep it to refine the mesh, and then use sensitivity analysis. I have to select this. Then I go to properties, and then it's already selected by default to do a sensitivity analysis with the imported field, which is the displacement field. So I click on OK and I start. So when I get the results, I would play the video back, but for now I think that's it, and then you'll get the results. So I'll pause the video, I'll start and pause the video now and come back when it's done. Okay, so simulation is done, and yes, we have our results. So here we have 9 modes, but we'll look for this is not the TML one, there should be mode 7. Yes, so mode 7 is still our fundamental mode, and then we have some errors here, but then it's because we do not have any surfaces defined. So now to see the shift, you have adaptive meshing also. I did not change my adaptive solver settings, so it's finished pretty quick. Now the mode frequencies, you have the new mode frequencies, you could check them, and then the sensitivities. So I think it's here, you see it. Yes, so this is the detuning of the frequency. Now you see that this is maximum 8.77.e minus 6 megahertz. Okay, now looking at the results, this is already quite small. So this is about 8.7 hertz. So I looked at the result and saw that okay, there was a mistake I made. So I would talk about the mistake, then make the changes, and then run all these simulations again, and then we'll get the result. So the mistake was here. Maybe you already realized it before the end of this video, before you got to the point of this video, but I did not. It's after I saw the result. So the mistake is for ear acceleration. Here it is it's 2.7 megavolts per meter, not 27 megavolts per meter. So it's 2.7 megavolts per meter, which means the value I'm supposed to be scaling by is calculator. So 725 divided by 2.7. 2.779278. So the square of this value is what I'm supposed to multiply by, not the other way around, because this is 2.7 e to 6 and 25 megavolts is 25 e to 6, so it should be 2.5 e to 7. So that was the mistake. So I've fixed it. I'm going to fix it now for the mechanical simulation. So I'm going to go for the mechanical simulation, and in the simulation, what should I do? Okay, I have to close this and get back to my 3D model, and then I don't trust updating this because I think it's going to break something. What am I going to do? Okay, I'll just click on escape. So I'm going to go here, and in my field sources setting, I'm going to put this value, the square of this value instead. Square, yes. So I could also look at that. I hope. No, I can't. I can't. Just want to confirm. Okay, so that's that, and then I would start the simulation again, and then after this I would import the displacement displacement field into the Eigenmode simulation again and run it, and then I'll show the new results. Okay, so now I run the mechanical simulation again, and then we see the displacement come up to 0.0141 millimeters. So that's the maximum displacement, that is to say. And then importing again into the Eigenmode solver. Where is that? Can we use this? Okay. Then we could go to 1D results, sensitivities, and let's see, displacement mode 7. So this is the mode frequency with displacement, and then so for mode 7 you see that this is so maximum, yes, so the 0.0007, which is 700 megahertz. So that's the Lorentz force detuning. So it's about 700 megahertz. In this paper it is 900 hertz. So now I don't know exactly the mechanical properties of the material they used, and I don't think I can find it from here. It's been a while since I last read this paper. So it's 900. So my best guess is that the material properties might be slightly different. Yes, but then I think maybe we could get the, if you go through the paper and then you see the material properties of the exact material that they use for their analysis or maybe measurements, then I think maybe we would have a closer result, although here it's listed as approximately 600 hertz, but I think that's because this is 900 hertz for Stephen cavity and then 500 hertz. Okay, no, this is for a long pulse. Okay, now this is different. I wonder how they got. I mean, here they said, I think maybe I'll have to take some time again to go through this, because here it is reported as 900 hertz and then here it is 600, approximately 600 hertz. But the result we got is 700.7 hertz. So I think it depends on material. That would be my best guess. But then if you find the material, then you could change the material properties of niobium, which is here. Materials, yes, then you could change the material properties of niobium. So double click. Okay, CST is misbehaving today. But then, okay, I think now. Yes, so we could go to mechanics and then, yeah, we change the material properties here and then the density, then maybe you get similar results. But yeah, that's how you calculate the Lorentz force detuning. I think, yeah, that will be it for this video. I have no idea how long this is, but it feels very long. But yeah, if you're able to get through it, congrats. That's how you calculate the Lorentz force detuning, and then you have some other results like the stress, strain, and all of that important things. So yeah, I'll stop this video here. And then I said I was going to do something else, but now I've forgotten. But okay, yeah, pressure sensitivity. Yes, in the next video I'll be doing pressure sensitivity analysis of the cavity. So yeah, till then, bye.